Today we're going to be talking carbon fiber versus fiberglass versus Kevlar, and which one is right for your application. Now, my background is in race car engineering, so I'm going to be talking more of it from a car perspective, but you can apply the same things I'm talking about here to boat building or anything like that. Now, I've manufactured quite a fair share of parts out of fiberglass and carbon fiber, a bit fewer out of Kevlar, but I've still done it. But perhaps just as importantly, I've been educated at a university level in how these materials work. So I'm going to try and share a bit of that knowledge with you and clear up any misconceptions you may have. Now, I'm not going to go into detail on how the composite structures work from a stress point of view, but if you'd like a video on that, leave a comment in the description below. Now, the most important thing to notice when you're looking at any material is in fact the definition of material properties. Many people toss around terms like strength and stiffness with little regard for what the actual effect of these is, and this is a really important thing when comparing these three composite materials. Strength is the ability of a material to resist a force. If you apply a force that is larger than the strength of the material will break. This is known as the ultimate tensile strength, UTS. Strength has no bearing on how far a material will deform, it only says when it will break. So if you apply a 100 kilo load to something and it breaks it there, then you can calculate the strength off that. What you need to calculate how far it stretches is known as the stiffness. Now, the stiffness of a material is essentially the ability of a material to resist deflection or deformation. I think everyone has a pretty intuitive grasp of what it is, but it's important that stiffness and strength are not related. You can have very stiff material that isn't very strong, you can have very strong material that isn't very stiff. And this brings in the next factor, which is called elongation. Elongation is basically how far the material will stretch before it breaks. Now, if you have more elongation, you can essentially get a tougher material because it will stretch more before it breaks. So if you imagine a plastic that's not very strong but stretches for a long way, if you hit it with a hammer, your hammer's probably just going to bounce off or deform it. It's not going to snap it. Whereas if you have glass, which may be a lot stronger than the plastic but doesn't deform as much, when you hit it with the hammer, it's going to smash into 1,000 little pieces. Finally, density is basically just how much a material weighs per unit area. Now that we have our basic definitions of what constitutes our material properties that we're interested in, we can now actually start to have a look at the differences between the materials we have available. Now, composites obviously have these fibers sitting within a resin matrix. Now, what that means is that we have a whole bunch of straight aligned fibers that are being held together by some sort of material. Now, in most cases, there's something like an epoxy resin. Because we're looking at three different materials that can all be used with an epoxy-based resin, I'm just going to be talking about the fibers, not the resin. We can go into that in another video if you want that. So the material properties that we're seeing today, I've collected from a combination of a DuPont paper on various composite materials, and also a bit of material data from MatWeb, which is a good resource for this sort of stuff. Let's have a look at the tensile strengths. The first thing here, and the thing that's going to confuse quite a lot of people, is that fiberglass is actually stronger than carbon fiber, and not many people know this. Now, the ultimate tensile strength is defined as a force over an area. Glass for a unit of area will be stronger than carbon and even Kevlar if you get S-glass. Now, the difference is there's two grades of glass here, S-glass and E-glass. S-glass is a much stronger but more expensive grade of fiberglass. Now, you can use that in really high strength applications. In fact, it's still used on modern aircraft, where they need something with really small thickness and they have to get something with a lot of strength in there. Now, if we have a look at Kevlar, Kevlar is also stronger than carbon, and we'll go a bit more into the whole Kevlar thing a bit later. E-glass, weaker than Kevlar, stronger than carbon. Now, E-glass is the regular glass that you get. It's pretty standard and run-of-the-mill glass. Now, if you have a look, all of these are stronger per unit area than a high-strength steel wire, and the reason that is because of the manufacturing processes that pull these fibers out into really thin, long filaments mean that they end up with a lot of strength. So why do people have this misconception that carbon fiber is the strongest thing that you can get? Well, it's two-part. One is it is light density, and we'll go into that later. But two is that carbon is incredibly stiff. Now, the big problem here is that people use interchangeably stiffness and strength when they, as mentioned before, are completely different. Now, high modulus carbon has one of the stiffest moduli of any material. It's insanely stiff because what it essentially is just a strand of diamond. We'll notice here that steel is incredibly stiff in comparison to these other polymers and glass available, the Kevlar and the S-glass and the E-glass. But again, we'll get into the density thing a little later on. The key thing to take away from the stiffness is carbon is incredibly stiff, but don't confuse that with strength. The second reason why people think carbon fiber is so good is its density. Now, if we have a look here, we can see that even though the fiberglasses were very strong in tension, their density is much higher than either Kevlar or carbon fiber. Now, Kevlar is the least dense because it's essentially just a sort of regular polymer sort of thing. Now, we can see here that in terms of relative strength to weight, Kevlar is the strongest in tension. Now, Kevlar is a very strong material. It's really good, but it does have its drawbacks, which we'll go through later. S-glass is stronger in strength to weight than carbon fiber. Again, S-glass is a high quality material. It's more expensive, but it is not weaker than carbon. Carbon is weaker on strength to weight than S-glass. Carbon is stronger on strength to weight than E-glass, which is why people think that carbon fiber has better strength to weight than fiberglass, because generally people deal with E-glass. What's interesting to note here, though, is the percentage it's up by is not that much. It's only about sort of 30%, 20%-ish, sort of like that. So if you were designing a structure that is purely strength critical, nothing to do with flexure, then in most cases, fiberglass is a fraction of the cost and not too much weaker than carbon fiber, which is an interesting fact for all you wannabe race car builders. Now, of course, when we look at the stiffness, the tables turn quite a lot. We can see here that the glasses have far less stiffness than the carbon fiber. We've got about a 5-to-1 ratio here of stiffness to weight sort of difference. Carbon is very stiff, as earlier mentioned, and we can see carbon is much stiffer than even the Kevlar that's available. And of course, we can see on the far side that steel does not even compete in terms of strength to weight ratio in this crowd. The interesting thing with Kevlar, now I was talking about how strong it is, but if we are to reverse the direction of our loading and put the material in compression, all the other materials do quite well. But if you have a look at this graph, you'll see that Kevlar loses a considerable amount of strength when you load it in compression. Now, what happens is you get a micro buckling of the fibers. Basically, you press on the ends and they flex out. And so Kevlar has almost no strength in compression. In fact, usually the fibers buckle before the matrix, which is quite an interesting phenomenon. What does this mean? It means that if you are planning on using Kevlar in your composite structure, say you're using it on your race car wing, you can only use it in somewhere where it's going to be in tension. So race car wing, think the top side of the wing. Plane wing, think the underside of the wing. In general, though, you can kind of see how S-glass may actually be the superior material for you in many of these cases, because if you've got an unknown loading direction, let's say it's going compression and tension, then the S-glass will give you the highest strength to weight available. Carbon is, of course, a good compromise here because it does have decent strength to weight and is, in some cases, more easily available than S-glass, because you don't want to end up with E-glass if you're trying to target that perfect strength to weight ratio. Now, the stiffness of the carbon doesn't come without quite a high cost. If we look at the elongation of all these materials, we can see that carbon has almost no elongation at all. Now, this is generic carbon fiber, and it's only got about a bit under 1.5% elongation. Problem with that is that it leads to a problem with material toughness. Toughness is basically defined as the area under a stress-strain curve. Now, what's a stress-strain curve? Basically, it shows how far a material moves for a given amount of stress. So if we assume brittle failure modes for all these composite fibers, we can see that the area under the curve is basically proportional to the elongation multiplied by the ultimate tensile stress. Now, with S-glass having that really high tensile stress, but also having that really high elongation, we can see that by far it is going to be the toughest of these materials. So, followed by E-glass, you're going to basically want to use glass fibers wherever you're going to experience like an impact loading, something like that, that you need toughness in your material. Kevlar is the second strongest on this, and the reason why it's used in bulletproof vests over, to say things like carbon fiber, is this sort of reason. Kevlar is also known for its good abrasive strength, which is why it's often used as skid plates on the bottom of race cars, and again why it's useful in bulletproof vests. Now finally, I just thought it would be interesting to throw a little thing of cost in. Now, on my race car, all the parts are fiberglass. Now, why do I do this? Well, it's on a budget, and generally speaking, fiberglass is about 1/7 the cost of carbon fiber. Kevlar is somewhat similar, usually a little bit more depending on who you get it through. The main thing to note here is the extra money that you've saved from not burning all this money on carbon fiber and just going with a 30% heavier structure out of fiberglass. And keep in mind that 30% isn't really a true 30%, because with the fiberglass, you actually only need a thinner layer of fiberglass for an equivalent layer of carbon fiber, which means you are saving mass
on your matrix and resin because it's not as thick. So in reality, you're only going to be seeing sort of like a 15% weight difference on a correctly designed structure. With that in mind, is 15% weight difference on your aerodynamic surfaces worth an extra $70 per meter? For most of you watching this video, I'm going to say that it probably isn't, and that money could be better spent elsewhere. Of course, if you're at the pointier end of the competition, then you should be using carbon fiber, because at this end, you're kind of not budget limited. The increased stiffness is going to really help, especially with aerodynamic surfaces that are close to the ground and you may not want flexing. Where would you use Kevlar? Well, to be honest, you probably wouldn't on most race cars. You might use it for abrasive surfaces on the underside of stuff, but then again, things like metal skid blocks are probably more appropriate here. If I'm honest with you, I probably would stay away from Kevlar in most race car scenarios. You can make pretty much everything you need out of carbon fiber and fiberglass.
So hopefully that clears up a few things about the nature of composites and what's good and what's bad for what you're trying to do. I hope you enjoyed this video. If you liked it, don't forget to subscribe to my channel and check out some of my other videos. And hopefully, see you next time.